interview. Okay. Okay. Start by myself. Okay. Just written in curriculum vitae. I was born in 1935, January 17th. Now, so I am 61 years old. And now, my former position is full professor of Kyoto University, Japan. And then I belongs to some Japanese university style laboratory consists of one professor, one associate professor, and 2 research associate, and then about 25 students, including doctor course and the master course student and the undergraduate course students. And then I would like to begin my personal curriculum vitae first. I was born at Himeji city in the middle part of Japan. It is very famous as a castle, Himeji Castle. It is now one of the national treasure of Japan, like the pyramid of Egypt. It is very, very extremely beautiful castle, symbolize Japanese Middle Age fort. But only 1 month I shift to Osaka, and then mainly I spent time in children age in now Korea or North and Southern Korea, mainly in Seoul now, because reason of at that age this country is a kind of colony of Japan. And after the Second War, I returned back to my hometown, and in 1928, I advanced to Kyoto University. I aim to. There are so many reasons why I choose chemistry, but I think in my child age, it is some kind of rocket or petroleum, fire. This kind of energy is mostly important for the humankind, because I have many experience. Of course, one of this is last Second War, and then just 1 year before I received the entrance examination, my living city is completely burned off by the so-called flame phenomena. Very dry and warm wind come from southern part, and then fire, and then whole city was burned out. So fire is this kind of fire is very important, but should be controlled very carefully. So then I choose to the fuel chemistry of Kyoto University. It was very famous as one of the mecca of worldwide sense of Fischer-Tropsch synthesis. So it is really important story. Fischer and Tropsch published their first paper in Bericht of Chemie in Germany, and then only just 1 year later, my former professor, great professor Genichiro Kita, started Fischer-Tropsch synthesis in Japan. And actually, about 1939, they established a very nice iron-based composite catalyst. It's composed of iron and copper and some manganese and boric acid and some very small amount of potassium as a co-catalyst, and supported on diesel or the atmosphere spray. This iron-based catalyst is very so excellent, has performance. It's almost comparable to the cobalt-based catalyst. And actually, the Germany used as an industrial catalyst. In fact, this iron-based catalyst finally was applied to the Fischer-Tropsch synthesis in Japan in the second war, during the second war in Hokkaido area. And they produced about totally 30,000 tons of this man-made petroleum was produced in this factory. But after the second war, this activity completely stopped. But before the so-called Sazol presses start to begin the operation, still in our laboratory continue the work of syngas conversion to make olefin. So, but anyway, after the oil supply is become very stable due to the foundation of a huge amount of petroleum field was found in Saudi Arabia area. But after the oil crisis, at that moment I already saw some successor of the Professor Kita, and I think of the idea, what shall I start to this kind of catalyst? All over the world, many researchers start to again the Fischer-Tropsch synthesis, and everybody think of. So about several years ago, this kind of technology was established very much. So, but after several years, if we tried again, so supplying the very sophisticated many so precise instrument and a lot of so catalyst science or theory, but unfortunately, in general, so in frankly speaking, not so much essential so research result cannot be obtained, because the most important reason I think is everything developed according to the so-called logistic curve. Someone said S curve, and indeed in this conference, the first plenary lecture of the first day given by the Maxwell, Dr. Maxwell of Shell Laboratory, he used quite often the so-called S curve. I called this curve logistic curve. And also, I noticed these facts about 20 years ago. And then I always use this philosophy in my lecture, and sometimes a kind of plenary lecture. After that, I have experience. So the James Ross of Air Product, Dr. James Ross, also used this logistic curves, and also the very nice fine lecture given in Tokyo Catalyst Conference 2 in plenary lecture, Dr. Kuzumano of Catalytica of the United States he used very much. Everything developed or so change along the logistic curve. But once this curve approached to the plateau level, there is so almost no chance to so develop much more. So if to overcome this plateau level, we shall prepare completely or new concept and new technology or new material is necessary. And then this new logistic curve exceed the former so logistic curve. I always think of this idea and then so conducted to my research work. And then, so it is a funny story. In Germany and Japan, in Fischer-Tropsch synthesis, as a catalyst carrier, both independently developed, but in both they use so Kieselguhr. Why Kieselguhr is the best support, catalyst support? After the second war, so the Department of Energy now, but Bureau of Mines of the United States tested in the so laboratory suburb of Pittsburgh, the Fischer-Tropsch synthesis done by Germany, traced, gathered so every Kieselguhr from produced in United States, but they cannot. They couldn't find out the much more better results because this technology almost have approached to the plateau level. And then, but this result was published in IEC in 1948 from American Chemical Society. But we can see this report. There is no reason why the Kieselguhr is the best support. But after the second war, I so started to this subject, and then finally found the meso macro bimodal pore structure is mostly rational to the so good catalyst because the mesopore part has a role of so supporting bed area for catalyst particle, and the macropore has a role of diffusion so for the reactants. Then if the meso and the macropore are balanced, we have a very nice catalyst. But unfortunately, if this concept is elucidated, but we cannot so good gasoline synthesis or petroleum synthesis is not improved very much. But at that moment, very surprising, epoch-making news we received. This is, of course, so famous, world-famous DSM-5, developed by Mobile Oil Peoples under the supervision of Dr. Weitz. This naming was, they said, zeolite of Socony Mobile #5. So this catalyst produced very famous, not only MTG process, methanol to gasoline, or many kind of very shape-selective catalytic reactions. And the feature of this pore is very unique, very so uniform size and three-dimensional pore structure is mostly so favorable to the purpose of the gasoline synthesis. And then, as you know, this technology was established combining with New Zealand's government, so-called MTC, mobile MTC process was found several years ago in New Zealand, North Island. But so price of crude oil then decrease. Unfortunately, this technology cannot be compete to the oil conventional oil refining processes. So the activity decreased gradually. But another point of view, this catalyst produced from methanol, gasoline from methanol contains aromatic-rich gasoline because very strong acid sites, methanol finally converted to aromatics, mainly BTX. This supports a high octane number. But unfortunately, most recently, people want to less aromatic gasoline because the aromatic compounds that cause of the oxidant or cancer reason. So now we requested non-aromatic gasoline. And because I noticed very important point, so ZSM-5 has a very excellent, many excellent performance, but one only serious feature is hydrogen transfer action. It is very important point. Hydrogen accompanied with forming aromatics cannot release so not easily to the gas phase, but easily move at the catalyst surface, and then this hydrogen is used to the hydrogenation of very important intermediate olefinic hydrocarbons to make paraffin, gaseous paraffin. It's a limit of gasoline selectivity. I think of the idea. Fortunately, ZSM-5 has a very wide range of silicon-aluminum ratio. Extreme case, as Union Carbide said, this is siliconite, so-called. Very huge amount of aluminum. So I extend this catalyst to so-called metallosilicate. It's a isomorphous substitution of aluminum by the other transition element. At the beginning of this studies, everybody believe this other element can easily incorporate it into the framework instead of aluminum. And then always I requested some serious question. How did you confirm this element can incorporate in the framework? It is not easy task, but now, as you know, everybody recognize this kind of feature. And I try to many kind of synthesis of many kind of metallosilicate, but of course it's some very important technique was necessary, because always zeolite kind of crystallization has been done very slow process, maintaining the temperature. For example, mostly famous example is ZSM-34. This ophiolite eleonite intergrowth crystal needs indeed 196 days for crystallization, keeping the same temperature. Even though the ZSM-5 sometimes 5 days, and sometimes needs 12 days. It's so, and then because people to synthesis people needs larger crystal to the convenience for the X-ray analysis, but the good catalyst needs not so perfect crystals. Then anyway, I reached to the our unique synthesis method, so-called rapid crystallization method. It is very easily not only economic by reducing very much the synthesis time, but rapid crystallization method affords a very small and uniform crystal size. And the more important point is hetero element component can be more easily incorporated into the frameworks, very stable, because sudden and very rapid crystallization occurred. This element, this kind of element, it's a precursor of crystalline, and then gradually crystallize to synthesize metal silicate. Then I made a lot of kinds of metal silicates. Some of them exert a very, very unbelievable, unique, and excellent catalytic performance. For example, iron silicate, ferrosilicate exerts unbelievable, extraordinary performance to olefin to gasoline synthesis. Almost for example, from propylene, it produces very high space-time yield, like much more 8 kilogram per liter catalyst per hour. Unbelievable large. It's beyond the limit of diffusion. Why this kind of big, large velocity can be realized? The reason why is this reaction involves autocatalysis. Then the concentration of propylene is if feed above some critical concentration, the sudden oligomerization of olefin advance, and then from gaseous propylene, the liquid gasoline come out without any gaseous products. It is marvelous technology. I heard from someone this kind of technology was industrialized by India. National Chemical Laboratory in Pune. They said they made this kind of catalyst and then named as their own name, and then applied to the industrialization. Anyway, and so famous recently, many kind of research has been done in the area of aromatization of paraffinic hydrocarbons. And then it is also famous gallosilicate, gallium containing MFI type silicate, or zinc silicate is some unique performance for paraffin conversion to aromatics. At the beginning, I believe, union carbide and the UOP, so-called very famous cycler process, I think they use the maybe ion exchange GSM5, but ion exchange GSM5, ion exchange method, this kind of ion is exposed and matrix of outside the channel, so it is easily move during the reaction and then deteriorate. Sometimes kind of zinc, it evaporate because the melting point of zinc is so low. But incorporated this kind of zinc or gallosilicate is very stable against so this kind of reaction conditions. So I believe out of many kind of catalytic process studied in all over the world, but most of them used this kind of metal silicate. And then, but I'd like to say some other prominent feature of catalyst is recently developed nickel sulfur 34. Just this paper was presented at the poster session in this 11th ICC meeting. This involves a very essentially important problem in catalysis because on solid acid catalyst, orogenic hydrocarbon, if start to convert from, for example, from methanol, then one molecule water so dehydrated and make a dimethyl ether, and one more water produce, and then olefinic hydrocarbon like ethylene. But normally this ethylene successfully oligomerate, and then finally if active solid acid is too strong, finally approach to the aromatic compounds. And then always this kind of aromatics also make a trouble of coke formation. So at the beginning of olefin synthesis, after the oil crisis, many researchers selected the very narrow pore size zeolite like Shabasite, 8 oxygen member ring, because the size of olefin molecule is just of this size. But fortunately, indeed, at the beginning of the reaction, olefin produced very selectively, like ethylene and propylene, but unfortunately, rapid catalyst deactivation occurred owing to the serious coke formation. Because this, for example, Shabasite has a very big cavity inside the zeolite matrix. Then in this big cavity, coke easily grows to make change into aromatic cokes. So, and also many researchers think of the idea to avoid this serious coke formation, they use GSM5. But the protonated GSM5 is too strong acid side to make olefin, because the olefin easily go to aromatics. So everybody think of to moderate this too strong acidity. They moderate it by basic material. Actually, in Japan, the big national project, they use calcium oxide as the basic materials. And then in China, they use magnesium oxide. And United States and France, they use phosphoric compound. And in France, they use, in Germany, they use boron. And in Saudi Arabia, they use barium oxide, like that. But by the by this neutralization, activity decrease so much. So it is necessary to maintain the methanol conversion to around 550 degrees C, very high temperature. Then the hydrocarbon, so once
Now,
prolonged, with the growth, and then it's cut by the law of beta fission, so-called beta fission. It means main product of the olefin component is occupied by propylene. Of course, propylene is important raw materials for petrochemical industry, but the most invaluable olefin, ethylene, is very little by this method. And so selectivity to C2, C4, 5 olefin is not so high. And also this high temperature, we cannot avoid the coke formation. On the other hand, if we use this purpose, iron silicate produce only ethylene and propylene at very low temperature, around 300 degrees C. And moreover, just I said, nickel SAPO 34 produce only ethylene exclusively from methanol. In fact, we observed was as high as 90% selectivity to ethylene formation from at 100% of methanol conversion. But about 6 years ago, this result was published from JCS Chemical Communications, and many researchers engaged in petrochemical industry or petroleum refinery attract this subject, and then they tested our result. But only John Muller Thomas of United Kingdom succeeded to reproducible results, and then they published a very long paper. But many people cannot realize reproducible data. So, but ourselves, it is not so easy task to obtain the 90% selectivity. Then we carefully start the very precise experiment, and finally approach the conclusion. Because this kind of very sensitive catalytic reaction needs very tailored designed catalyst. And finally, so example, crystalline size and distribution of the crystalline and acidity. And then we approach to the very reproducible procedure. That's the result presented in my lecture presentation in this conference. Besides those energy and raw material for petrochemical industry, we are now in our effort was focused into the global environmental programs. For example, mitigation of carbon dioxide. Of course, carbon dioxide is seems to be very cause of the global warming. And then we use so many proposals are presented to how to decrease the accumulation of carbon dioxide, or how decrease the use of fossil fuel combustion. mainly political strategy, but it is very difficult to realize. On the other hand, many researchers already started to research, but the mostly problem is carbon dioxide is final products of the organic compounds to so by combustion. It means thermodynamically it is no value. So if we use these compounds to the some variable compound, it needs very expensive energy, hydrogen. So this carbon dioxide problem is how we can get hydrogen, huge amount of hydrogen, how we can get the cheap method, but it is very difficult. Many of them think of the use solar cell, and then this generated electricity. They decompose water into hydrogen and oxygen, but it is very difficult to economically adjust technology. But maybe it will be achieved in the very far future. But our catalyst researcher, how we can contribute this subject. Then we started to the extraordinary high reaction rate of methane reforming, because methane reforming, steam reforming is now industrially conducted for the purpose of mainly ammonia synthesis and methanol synthesis and other usage. But using a very sintered nickel catalyst, it is operated at around 900 degrees C, very high temperature range. And then the serious coke formation cannot be avoided. So to protect this coke formation as much as possible, they use excess steam. I think about almost twice as stoichiometric reaction ratio. So it is an energetically not a good process. Besides, they use excess steam. Once formed hydrogen and carbon monoxide, again this carbon monoxide react with steam, finally produce only the final products of this conventional technology is hydrogen and carbon dioxide. So many criticisms come out. In order to reduce the carbon dioxide, so if we make synthesize hydrogen, then carbon dioxide again produce accompanied with hydrogen. It is nonsense. But I think this kind of criticism is based on the knowledge of the conventional catalyst technology. We are now apply the non-linear effect phenomena in catalysis to the design of new type catalyst. It non-linear phenomena means spillover effect. Spillover effect bring about the surprising effect in catalysis. For example, we use nickel-based and cellular small amount of celia and very small amount of platinum as a co-catalyst. This kind of catalyst exhibited a very high performance for steam reforming of methane and carbon dioxide reforming of methane and partial oxidative reforming of methane. But if we increase the space velocity of reactant gas, as in very naturally the combustion of methane is decreased. But if we modify very small amount of rhodium by this catalyst, we can get very surprising result even at a higher space velocity or a very short contact time as a millisecond order. We can obtain the hydrogen and carbon monoxide almost stoichiometric ratio, and conversion of methane can be obtained almost the reaction equilibrium. It is surprising. So it's we can realize a millisecond order reaction, very short contact time. In order to compare the conventional reaction is now operated under some medium pressure range, and the contact time about 30 seconds. If we convert to atmospheric pressure, it's a 3 milliseconds, 3 seconds. It means 1,000 times increase the reaction. It is very so important because if we can increase reaction rate 1,000 times, we can decrease temperature much lower than conventional one. And then, for example, 500, 600 degrees C, we can use the waste heat of the large industries. No additional fossil fuel combustion. We can save the fuel very much. But one more important problem is so reaction equilibrium. We cannot exceed the conversion. How we can overcome this so limit? Then we can think of the idea to combination of the two reactions. One is of course reforming reaction, and one is a catalytic combustion on the same catalyst surface side. Because reforming catalytic reaction is a large endothermic reaction. So if reaction rate is too fast, the heat supply from the reaction wall cannot pass through of the reaction. So, but if we can supply the reaction heat by the combustion heat on-site supply, then actually in practically we succeeded to overcome the reaction equilibrium limit by adding very small amount of more combustible hydrocarbon like ethane. It of course contains in natural gas. And then ethane can be easily combusted at lower temperatures than methane. And then heat supplies very much. And then of course produced carbon dioxide, water successfully react with excessive methane. So final product, every product is water, hydrogen and carbon monoxide. Then even at around 400 degrees C, if a reaction equilibrium between by the carbon dioxide reforming methane is about only 10% of methane conversion. But by this combination, actually we can obtain the more than 80% conversion of methane at 3 or 4 milliseconds of very, very short contact time. And then this catalyst, novel catalyst, is now so attract attention as one of the hope of the so cheap and rapid hydrogen production. And then we can extend this technology if we can use methane and carbon dioxide, then successfully it can be converted into syngas, then introduced to the methanol synthesis gas, methanol synthesis catalyst, make methanol, and then seriously connected reactor, this methanol can be converted into gasoline, even from carbon dioxide. It is very important new technology. And actually, now in my laboratory, carbon dioxide can be converted into gasoline very, very effectively. If we obtain the petrochemical industry, we replace so second reactor catalyst, and then we can obtain the ethylene and propylene or aromatics. Appropriate, according to our object, we can change the products. And then another recent so very interesting catalyst innovation is purification of NOx exhaust from the contained in the exhaust gas from the diesel engine or Rimban engine exhaust, because these components contains large excess oxygen in the gas phase, different from the gasoline engine. So far, so-called three-way catalyst, mostly effective to the effective catalyst for the gasoline engine. Almost every car in United States, in Japan, were equipped this catalyst. But unfortunately, this kind of catalyst is not effective for diesel engine exhaust. Many researchers studies on this subject more than 25 years, but nobody succeeded to this problem because the catalyst surface easily oxidized, and then so disappeared NO conversion. But about 5 or 6 years ago, Professor Iwamoto of Hokkaido University announced so small amount of hydrocarbon, if so exists in the reaction gas, it can be so realize the conversion even in excess oxygen condition. I think it is almost same time we also think of this idea, and then so present annual meeting of Japanese Catalyst Society, Japan. But anyway, about 5 or 6 years ago, suddenly, explodingly, this subject extended to all over the world. So many researchers engaged, but still not yet industrialized. Because most important point of this technology is if in laboratory we can observe the good result, but in practical use as honeycomb engine, it is some very serious condition, high temperature, and then coexist of about 10% of steam. Then this kind of thermal steam condition, many of the ceramics or catalysts easily deteriorate by the phase transfer and sintering, so many kind of reason. So this is it's a serious problem. But if we can contain active catalytic component in the framework of catalyst, then again we can obtain the very stable catalyst. So, and then more important point, we realize very stable catalyst as the use of so metal silicate catalyst. But I would like to point out a very important concept towards the next century is, as you know, everybody that this century is simply says, I believe, linear phenomena. Only so treated linear phenomena. For example, Langmuir, Professor Langmuir proposed so-called Langmuir monolayer adsorption theory in 1990. And then this theory extends to the reaction kinetics, so-called Langmuir-Hinshelwood reaction mechanism. But established condition of this theory is very limited conditions. But nobody forget the establishment conditions. Everybody think of the idea to explain this so classical theory. But this classical theory is strictly saying only the very limited condition, so-called in linear phenomena. But so it is very successful for the analysis of on the kinetics because in conventionally catalytic reaction is frequently used for the synthesis of some important goods. In this case, very considerably higher concentration compounds react with each other on the surface of the same catalyst by molecular reaction maybe. Adsorbed species A and adsorbed species B react with meet on the catalytic surface and change products. But so it is a bimolecular reactions. So and then always fit even in very simplified theory. But in case of global environmental problem, for example, NO, nitrogen oxide in the exhaust gas of diesel engine, it's very, very deviated reaction conditions. The aimed component NO exists in ppm order, but so disturbed and unfavorable compounds like oxygen and water is 10% or more. It's a big difference. Then, of course, already, so the establishment condition of this non-linear phenomena, like Langmuir-Hinshelwood reaction mechanism, is far away. But everybody think of the mechanism according to the conventional mechanism. So, we consider the absolutely new concept, real heterogeneous catalytic reaction mechanism. Then we can solve the real mechanism. Why this kind of unreasonable diesel engine exhaust can be converted, so NO can be converted to these conditions. But still, this argument is not so concentrated. Many arguments are discussed, still argument. But right on right. Maybe
Tape almost done.
Okay, then replace the new one. Okay. I'd like to add some more very interesting and important results towards the next century. We should use much more the non-linear phenomena to the catalyst. For example, our recent research achievement, for example, I would like to say shortly. Everybody know the first generation methanol synthesis catalyst was established in Germany, BASF, in early 1930. The catalyst component is zinc oxide and chromium oxide mixed by simply physically. But this catalyst needs high temperature and high pressure to synthesize methanol from syngas. And after 30 years later, it means new logistic curve. So-called low temperature methanol synthesis catalyst was established by ICI of United Kingdom. This catalyst was prepared by so-called co-precipitation method. And then still now, all over the world, this kind of catalyst is used as an industrial catalyst for methanol synthesis from syngas. But the multi-metal oxide components catalyst, if even we say the co-precipitation method, but the equivalent point of metal oxide, each metal oxide is different. So only apparently uniform, but non-uniformity is principally exist in this kind of method. Especially we can easily have experience precipitation material during the course of washing process. Approaching pH 7 neutralize the sticked particles disperse, segregate each other, and then non-uniformity comes. So if the real catalytic active site locates borderline of the other components, oxide components, then separate, and the effectiveness factor of this catalyst decrease very much. So we improved first by the different methods, so-called uniform gelation method. It means concentrated nitrate metal nitrate solution, a mixed solution is contacted with gaseous ammonia with a thin layer of liquid, and then totally change into gelous state. Then we dried carefully, and then summary decompose directly, so we can avoid any washing process. And then making ammonium nitrate. Then ammonium nitrate very easily decomposed at around 200 degrees C. So we can obtain the very uniform and high surface area materials. The necessary condition is use like aluminum nitrate, because this kind of material make gelous matrix. It's a necessary condition. But anyway, by this method we can improve the methanol synthesis activity 50% increase. But 50% is not so much. Then second step, we establish a third generation methanol synthesis catalyst, then it is very important. I think for my almost 40 years experience of catalyst synthesis, most necessary things is so principle is balance of acceleration and retardation. If acceleration only, it is make a unstable at a high reaction rate. For example, methanol synthesis most important things on catalyst surface is intermediate oxidation state between cupric oxide and methyl copper. But if reaction rate enhanced very much, if hydrogen supply is only hydrogen supply is enhanced, the surface of catalyst incline too much reduced state. So finally deteriorate. We cannot obtain maintain the optimal condition. So very important point is it's a new concept. It's balancedly join the opposite for so-called inverse hydrogen spillover effect. Normal hydrogen spillover effect by the combination of some precious metal like palladium, and then the inverse spillover effect is gallium oxide, for example. Gallium oxide can spill over hydrogen inversely. So combined with balancing, then we can operate very higher reaction rate, still very stable the optimal condition, and then as a result we can realize in practically 8 kilogram methanol space-time yield per liter catalyst per hour. It means more than 10 times or 20 times 10 to 15 times of conventional industrial catalyst level. So we believe this kind of catalyst will become the third generation methanol synthesis catalyst. Why we investigate this subject is there is some reason. Just as mentioned before, the methanol to hydrocarbon conversion or olefin oligomerization involve autocatalysis. So the methanol or olefin concentration in gas phase must be higher, much higher. Otherwise, we cannot obtain the gasoline selectively. So that's why we aim to improve the methanol synthesis catalyst. By this way, so the balance of acceleration and retardation is not only catalysis, but always it's important even in our human life. I believe any time the good catalyst principle is very similar to the best behavior in the human life. And then for example, so many kind of application still advanced, and then yes, but anyway, most important. Another big area is a computer simulation. Application of computer simulation to the catalyst design or catalyst understanding. It is very impressive story. About 9 years ago, first Boleskov Memorial Catalyst meeting was held in Novosibirsk, former Soviet Union. And then I was invited from Japan with Professor Tamara, and then gave a lecture here. And also John Thomas attended this meeting. And then he gave a very impressive lecture. Just, it is my first experience to hear the computer graphics applied to the catalyst research. In his case, so zeolite is a very nice target of computer graphics. And then in his lecture, very beautiful computer graphics missing captured inside them zeolite channel structures. Anyway, after I returned back to to Japan, I started to introduce my laboratory, big facility to perform the computer simulated research, and finally we can obtain from the government some special fund, and started to application of catalyst research, computer simulation. At that moment, my research associate professor Akira Miyamoto, you know him very much. He engaged this subject mainly, and then as a result, he promoted to the full professor to move to Tohoku University, and still now he continuing this research very extensively. Of course, but in my laboratory still continue this work, and already found a very, very impressive results. For example, we can do very not so easy task to measure the diffusion constant in microporous crystal material, because diffusion process is very, very slow. And if to promote diffusion rate, if we elevate temperature, the reaction accompanied. But if we can conduct in computer simulation, we can do very much using molecular dynamics or molecular field, and then every potential can be calculated to and then the effect of the moving molecule. Then we can extend to the, instead of experimental, we can obtain the diffusion constant for different kind of hydrocarbons, or not only hydrocarbons, but different kind of theoretical materials, for example. And of course, this kind of technology can be extended to the evaluation, estimation of thermal strength of framework. Then we found, for example, beta type zeolite is very strong against high temperature. And this result already applied to the in practical catalyst of Rinban Dinox catalyst in Osaka Gas Company in Japan. We can differentiate the strengths or thermal strengths of framework very easily. And then other project is a very interesting subject is evaluation, estimation of acid strengths. So far, we can only the measurement of ammonia dissolved profile, so-called ammonia TPD, is only the effective way to evaluate the acid strength of the solid acid substance like a zeolite. But it is, everybody notice, it is very, the information is very qualitative. Only the peak temperature, high temperature peak is so large or small, or peak position temperature was lower or higher, something. Still, this information was very important. But using Monte Carlo method, it means like the probability law, we can experiment on the computer ammonia, so adsorption and resorption, recycling, a very huge amount of so repetition of calculation, and finally we can obtain the surprising facts. For example, protonated GSM5, 8 GSM5, it's the acid strength is surprisingly very so localized. Some points, very strong, simple acid strengths can be obtained in each unit. Why surprising? But many experimental facts can be explained by this result, because Dr. Olson or Mobile people presented the paper and emphasized the content of aluminum in GSM5 strictly proportional to the acid strength, or so-called alpha value, normal hexane cracking. It means aluminum content proportional to the acid strength. But why? So other zeolite like Hodgesite type zeolite, not so good relationship. But by this computer simulation, we can understand the acid strength in each so crystal unit localized only one point, concentrated. That's why the reason of hydrogen transfer reaction occur. I think like analogy, it is a black hole of space. Everything approach to the so strong acid sites. Then, if aromatization occurred and hydrogen so evolved from the molecule, but olefinic hydrocarbon so exists very near of the acid site. So hydrogen easily shift to the olefin, and there is no chance to evolve. But the other metallosilicate, like gallosilicate and iron silicate, it's different from each other, but acid strength this so located, not only concentrated to one peak, dispersed some parts, for example. It is very interesting. Of course, and the extent of this ammonia adsorption, we can extend the adsorption calculation into to the water and reaction, some reaction products, reaction, carbon monoxide, carbon dioxide, and then results of this adsorption data can be applied separation technology. Of course, isotherm, isobar can be obtained theoretically. And then recently found very important facts to so carbon dioxide and nitrogen separation, and oxygen and nitrogen separation by pressure swing adsorption. We can apply the result of and the capacity of water adsorption is one of the reasons the so steam resistance. For example, aluminosilicate GSM5 has if we compare another conventional zeolite, GSM5 has a very less affinity for steam. So high siliceous materials. But still, if aluminum content is high in GSM5, it has some significant affinity of water. But for example, cobalt silicate has a very low affinity for steam. Then we almost conclude, this is the reason why the cobalt silicate is extraordinarily high resistance with steam and high temperature. So people of air products like John Armour, Dr. John Armour and his co-workers presented a paper without reason, the cobalt in ion exchange GSM5 is exceptional high stability for against high temperature and coexistence of steam. That's why we can, of course, experiment is always most important, but sometimes very difficult experiment can be assisted by the computer simulation with computer graphics. So, not so much time, but I almost told my think and philosophy of my research work.
How does education compare in Japan today to when you were a student?
Yes. Then, yes, it is very important things. But if you allow me, I would like to continue this interview after the lunchtime. Okay?
Okay.
Yes. And then always hope the good relationship between all over the chemists, especially catalyst researchers. And then, of course, United States is mostly powerful and important country from the viewpoint, not only from viewpoint the result as industrial catalyst, but any other reasons. But also Japan is also most important partner. So I would like to talk this point in the second part of the interview. Okay. Okay. Closing of my former part of my talk, I would like to introduce recent forthcoming program that we are preparing. One is this. You can see the very easily understand our logo, ICCDU4. It means International Congress of Carbon Dioxide Utilization, fourth international meeting. And this logo, I made by myself. You can easily can understand it's a CO2 design, and then imitates a globe model, and then this is a symbol of Japanese mountain Fuji, and then written in keep globe clear, because in my child age, in especially water, the color of sky was very dark blue, but we cannot see this kind of clear color in recent years because a heavy industrialized and always air atmosphere is something contains very small aerosol reflects light. We cannot see anymore the blue sky, except only the beginning of the July or beginning of January, because everybody start to produce such kind of activity from the factory. So I hope, our hope, and then I think about 300 persons come from all over the world. And then discuss how we can protect our global clean. And the second one is this is somewhat symbol flag of Japan. But as you can see, catalyst surveys from Japan. It will be published next year, 2 volumes per year, and started from next year. For a long time, it was requested that Japan has their own language, and then the grammar and so Japanese language cannot so easily understand for Western developing countries people. But and there are so many so scientific results published, but unfortunately only by written in Japanese. And then we can recall so many years ago, a lot of papers, almost all papers in chemistry field published from Soviet Union are translated into English. But everybody maybe recognize that recent research activity in Russia and decreased very much. Maybe due to the reflects economic state. I visited so many times in Russia, but unfortunately compared with in case of Japan, there are no good modern facility in laboratory, and I think it's reflect. So this is everybody want to know the result developed done by Japanese in English. So this is kind of survey articles, not only survey but mainly survey, and already so first authors for first volume settles, and then now I am so president of the Catalyst Society Japan, and former president Makoto Misono and Yoshio Ono. We are 3 so editor-in-chiefs, and beside our chief editors, many domestic so editorial boards and also international editor, so advisors. So you can expect the effect of this activity. Then you can catch our research activity much more easier. Okay, so I advance to the second part of my talk. Maybe we from the Western people, sometimes thinking of Japanese is not understandable, somewhat unclear. But not always our thinking is not so academic, scientific. But as I talk in my at the beginning of my talk, maybe next century, so the non-linear phenomena or fuzzy phenomena, another so target for the research or thinking. Otherwise, linear phenomena already almost so finished to study during in this century by a lot of effort of humankind. But still remains very huge area, almost non linear phenomena. It cannot be easily cannot express by derivatives, but some other approach. But quite often we faced, even in lifetime, unbelievable things or not so easy solved things. So, and then we shall consider even not only target, but the person, researchers, to make some free thinking person. This is an educational problem. I don't know exactly in United States, but several years ago, there is a famous discussion published in Chemical Engineering News from American Chemical Society. It was held in California, Berkeley, your university. Sam Buddha and Alex Bell and James Ross from Air Products, and maybe some other person together and discussed the anxious of the future of catalyst research in United States. And then they pointed out a lot of difficult problems, because as Heinemann told in his plenary lecture in this conference, reflecting, recalling 40 years in the past. Catalyst is unbelievable, undoubtedly important for the industry. I think about more than 80% of chemical products depend on the catalysis. But unfortunately, a very few, even in sense of mass and price of catalyst, produce huge amount of products. And then the better catalyst has a longer catalyst life. It means there is almost no economic merit or advantage for catalyst itself. So, this point is a very important point. On the other hand, many polymer products or engineering plastic or organic synthesis, there are so many tasks to studies. So a lot of students or a lot of researchers inclined to the field of the organic chemistry. But in organic chemistry and catalyst field, people don't write study so much. But this is a very big contradiction. In industrial size or humankind, it is very, very extremely important. But people engaged directly this kind of matter are very, very few. Always, catalyst is working on the central part of the process, chemical engineering process, but it's some kind of black box. Not so many people contact with this matter. This some secret feature of the catalyst cannot gather the young, brilliant students. But one more very important and delicate problem exists in this problem. For example, many researchers in catalyst field of course, naturally think of the very, very fundamental surface science is necessary to design the good practical catalyst. And then, of course, in United States, very famous professors engaged in this, also in Japan. Rather, number of this surface science researcher is rather so larger than the researchers engaged to develop the practical catalysts. This is troubles, some troubles. Someone said, some American catalyst engineer said several years ago when I invited to the Florida conference. It's a very famous one. Mainly Professor Drago of Florida University organized this meeting in each year. And about a few lecturers are invited from all over the world, some modern topics. Others, mainly the researchers come from company of United States. And then at that moment I was invited as the topics of paraffin aromatization. And one more lecturer was invited from Hamburg University in Germany. His name is Professor Kaminsky. So his innovation of the so-called Kaminsky catalyst for Portland polymerization or metallocene catalysts. And then at that moment, some researcher of United States, he belongs to private company, complains very much. He said, frankly saying, too much so fundamental, so surface science is not produce so good catalyst in practical. So, and then if so, brilliant students does not choose this area as his life work field. So it is some crisis for the good researcher in this field. Even I don't know exactly in the state of university in United States. In Japan, normally field of catalysis is called catalytic chemistry. Catalytic chemistry. It means catalyst research is so put as one of the field of big chemistry. So many reconstruction of organization, catalytic chemistry become very minor existence, and then every restructuration of the organization then decrease. It is very serious status. So I propose that to solve this big contradiction, we should make a restructuration of the study field. I think or I believe catalyst, so-called catalytic chemistry, is not only a very minor division of chemistry, but very big category, almost the same as or more than chemistry, because catalytic chemistry, catalytic study and Yes, it's involved not only chemistry, but also surface chemistry, surface science, and reaction engineering. So many fields of so studies involved. So I propose, but I don't know. But maybe in English. I asked during my stay in Russia. Uh, we, so is there a word corresponding to chemistry? Maybe nobody knows. Always said catalytic chemistry. But like as a single word, catalystry, there is no, I never heard this kind of words. So if a chemist means, so researcher, he is studying chemistry. But corresponding words, I don't know in chemistry, catalyst field. So, anyway, firstly, deconstruction, destruction of this academic field is really necessary. I think so. And then another point of view, there are so many journals related in catalysis, like this one, and so Journal of Catalysis, Applied Catalysis, General and Environmental, and Molecular Catalyst, and Catalyst Letter, Catalyst Today, Catalyst Topics, so many. And then not so happy things, so-called index. So what's impact factor of the journal is not so high compared with nature and science. So some unification of this journal may be necessary, but how we can so improve this situation? So someone said, or someone thinking, and then during this conference, maybe yesterday, some special session D was settled, and then discussion of the future of the catalyst and the catalyst researchers discussed in panel style. Unfortunately I have no chance to attend the meeting, but some participants said to me, it is really important, the philosophy of the catalyst, not only the detail, but the philosophy or principle is should much more told and discussed each other. So, of course, there are so many excellent education people exist in each country. Very proud and honorable person. And then, fortunately, in my country also exists. This is before Meiji Revolution. I think about 130 years ago. So named Shoin Yoshida. He's a very brilliant person, and then even 10 years old, he taught a lot of things to the young samurai. And then when he grows, he had a private school, and only 1 year and a half. There are so many students come to his school, and then many of them contribute to the modern Japanese government in Meiji area. It is very so interested so facts to consider why such a so very fluctuated so facts happened. Only so Yamaguchi prefecture is a so western part of the very small prefecture of Japan, and so Hagi city is a small town. But only 1 year and a half, so many important, distinguished persons come from this school, and then support or so establish the Japanese so modern government, and then behave to the so modernization of Japan. So I think always this is some original point of education. I understand. He didn't teach maybe not so concrete facts, but his effort is concentrated to each principle, guiding principle. And then if a student catch this guiding principle and then adjust his ability and then apply it freely for each way, then very variety and so attractive so talent so growing up. I think this kind of so education is now recently absolutely lack. Everything so systematized. So very stereotype students come out from the school. It is very trouble. Because I stayed in Kyoto University already 41 years. And then I so recalled past 40 years. Now in our neighbor, very so sophisticated modern instruments, so many. But so thinking in my mind is decreasing for some students. It is very serious so situation. If we recover the so in education like showing Yoshida, I think more fruitful and more attractive field of catalysis will come back. So in my lecture talk, I always taught so at the beginning of Fischer-Tropsch synthesis, so achieved by my former professor, Genichi Kita. One of his students, undergraduate students, Shinjiro Kodama, come to his laboratory, and Professor Kita asked Kodama, in your so graduate research, you should so find out the excellent co-catalyst for the Fischer-Tropsch synthesis. And then Shinjiro Kodama studies about only the 20 or 21 years old student. And then within a very short period, he found a great so positive effect on the Fischer-Tropsch synthesis is by done by the smaller addition of a small amount of magnesia and thorium oxides. And then he wrote in his graduate research report, this result will transfer to the German technology, and then they incorporated in this component in their industrial catalyst for Fischer-Tropsch synthesis. Germany make 10 factories during the second war, and then they produce 1,300 tons of man-made petroleum made by 10 factories using cobalt-based thoria and magnesia supported on Kieselguhr. And then it is some other interesting story, I think, of German people like Hans Schultz, Professor Hans Schultz of Karlsruhe University, complains to me. Everybody is called Fischer-Tropsch synthesis, but don't forget one more important person, Professor Pichler, almost cobalt-based catalyst was prepared by himself. And then it is very symbolic story. Also, you know, the very famous one is Dr. So in case of ammonia synthesis, it is called everybody by Haber-Bosch technology. But one more, don't forget, Dr. Schmidt,
Metash?
Metash. Most of the catalysts are prepared by himself and by his co-workers. Always, catalyst is most important, but always this kind of treatment. It means catalyst research work is, since preparation of new catalyst is firstly developed the new synthesis, just fit synthesis. But many catalyst researchers, especially in chemical engineering course, they import from the industry or somewhere catalyst, and the only analysis or characterization. And of course, analysis and characterization is not so responsible for the results of the reaction. So it is rather easier to make paper. Or only synthesis of material is not so difficult task. Prepared and then determine the new products by using an X-ray diffraction pattern or scanning at the microscope or something. But catalysis is an indirect process. If the catalyst is prepared one, is very beautiful, but it doesn't work good. It's no meaning. So always catalyst researcher should engage from the preparation and the characterization and the application of the reaction. This balanced cycle is absolutely necessary. But unfortunately, such kind of researcher in catalyst field is not so much. So I think this kind of direction should stress much more in the next century or future. So objective studies is necessary. Reflect of this situation, Nobel Prize is founded by Alfred Nobel and started this 20th century first Nobel Prize in chemistry field, of course, Fanthoff. And in physics area is Röntgen, as his foundation of X-ray in 100 years ago. And then at the beginning, very applicable, applied source results are given for them. For example, so many, related to the artificial diamond synthesis. Moissan, he received the Nobel Prize for the result of high pressure, something very practical things. But recently, especially in chemistry field, we don't know except Tigranata. And then in 1981, Professor Kenichi Fukui, he was a professor of my same department, received the Nobel Prize with Professor Hoffman of the United States as a result of frontier electronic theory. And then this naming was made by my former professor Haruo Shingu. He was associate professor of great Geis Kita that I talked to you. And anyway, in 1983, I visited Princeton research laboratory of Nobel. Just at that day, White was retired Nobel, and then to go to Switzerland to deliver some lectures. But he was waiting for me, my visit. And then I heard from someone he was nominated to the Nobel Prize as a result of foundation of GSM-5. But unfortunately, he didn't succeed. I pointed out, very sorry. I believe this kind of material, epoch-making material, is really correspond to the result of the Nobel Prize. But also he said, it was very sorry. But instead of them, Parkin Prize, American Chemical Society evaluate his works and then give a Parkin Prize. And then I think after Kenichi Fukui got the Nobel Prize in this quantum chemistry field, about 10 years, experimental research work in chemistry is not so bright compared with theoretical chemistry. And many brilliant students go to theoretical chemistry. So I think Nobel Prize, the value of Nobel Prize or significance of Nobel Prize is even this kind of famous and important prize, the value is approached to the plateau. So everything developed in this century, once recalled very carefully and examine the true value, and if necessary, we should change in style towards the next century to survive for the humankind. Otherwise, if we continue the style of 20th century, maybe we cannot so solve the very so serious environmental problems. Next century, maybe we produce in this century by the for the sake of big effort for petrochemical industry, for example, so many clothes and goods, high quality goods, and even also, of course, electronic products are flood all over our neighbors. But each of them consume very much energy. And Asian people like China and Thailand and Malaysia, these people who lives in those countries also request their improvement in lifestyle. But every this kind of improvement needs surprising large energy consumption. So everything should be considered within few years before 21st century. Then we can survive in the more longer future. Anyway, to protection of environmental circumstance, the role of catalyst is much more increased. But evaluation of the world and many important distinguished person in government is not so much. So I would like to propose every catalyst researcher, not only the just in front of the target, but also this kind of guiding principle for the future of humankind should be discussed. And then so many brilliant people should be joined to this area. Otherwise, ultimate destroy of the global will come suddenly, because you know the catastrophic theory. Catastrophic theory is founded René Thomas of French. He had a great mathematician, received the Fields Prize in 1986 or something. And in early 1970, he proposed catastrophic theory. It is after Newton's differential and integrals. But Newton's differential integrals are only treated linear phenomena. But there are a lot of non-linear phenomena exist in the neighbor of our life. But René Thomas' catastrophic theory can solve a lot of non-linear phenomena. But this theory indicates if we should treat or improve within the what shall I say in English, within the first beginning behavior, just otherwise sudden catastrophic change. If the phenomena exceed some critical point, we cannot protect anymore. We faced this kind of, we really approached this kind of points. So Professor Krylov of Russian Academy of Science, he attended this meeting also. We shake hands with him. He has an opinion. Every indicates concentrate to 2030s because for the increase of mankind, increasing across some logistic curve that I said before. But logistic curve, if we write the ordinary scale, it's S curve, seems to be S curve. But if we take a logarithmic scale, it can be linearized. So we can protect those surely estimate near features. So population of globe is estimated by this curve. So then people increase, number of people increase, but the increase of food and the increase of high quality energy is very slow rate. So he said, the minimum dangerous point will be coming just across every indicator across 2030 years. So I think we have not so much years times left in the critical point. So now I am a president of Catalyst Society Japan, and then I think a researcher of Catalyst in Japan, the member of this society, 2,500. I think maybe the scale of this researcher maybe followed by United States. Other countries much more small size. Maybe European Union countries together totally about 1,000, 2,000. So, but even so, a lot of researchers in catalysis in Japan, they are too much inclined to surface science. Okay, so maybe my consideration, many of my responsible person in United States also has this kind of anxious, and then many kind of international meeting and symposium will be held, but never this kind of international meeting has opened. So for the future, so I don't have weight. So I would like to start even only very small step, because our university retirement age is 63. My retirement age is now approaching. So I decide just during this conference, my retirement ceremony will be held in March 20 and 21st of 1998 in Kyoto, beautiful Kyoto city, and then the small but concentrated international symposium will be held in Kyoto International Congress Center. And then the celebrating banquet will be held in Kyoto Hotel. And then the feature of this symposium and ceremony is different from the conventional one, because almost conventional ceremony was held after retirement, 2 months later or 3 months later. And neighbor professor cooperate and then prepared everything. But in my case, absolutely different concept. Myself, during my position of full professor, but very near of retirement date, because the end of March is retirement. So I organize this kind of important symposium to talk philosophy towards 20th century in catalyst research, and then told and discussed with each other together, so that lecture already some already selected, so time is so limited. But from Japan, for example, Makoto Misono, former president of Catalyst Society, and Yasuhiro Iwasawa, he gave a very beautiful plenary lecture in this conference. And one more other is Eiichi Kikuchi. He belongs to Waseda University. Waseda University is a private university, but he's one of the leading catalyst researcher in Japan. From outside, several distinguished researchers, and then told together with this future and the philosophy of the catalyst. I believe this kind of positive philosophy is becoming more and more important. So finally, in my talk, I would like to express my sincere thanks for Professor David Barton of California University of Berkeley, to have this kind of nice opportunity to me. Thank you very much for your patient attention. So I finally add some small comment. Apologize for the audience if I can talk by my own mother language, Japanese. I can talk much more delicate, but this is some problem. Always American or Western people who can speak English as a mother language, should be careful for the foreigner who cannot speak English so fluently, because always he can express his philosophy or his expression, maybe his own ability lower than about 20 or 30%. So, if you can impress from the context of my talk, please give apologize. So give me some error or misusing of grammatical using. But if I have time in the future, carefully reproduce this kind of philosophy or thinking by more careful choosing the good sentence or good words, and then you can see and understand much more Thank you. Thank you very much. Okay. So please close.